it's true that if you directly compare a GPU to a CPU on the GPU's home turf, if you're rendering a filtered anti-aliased modest polygon scene on there, the GPU is 50 times faster than a CPU core. It's just way, way out there. But that is kind of marketing literature, benchmarking best case reality. We have several data points now that when you come at it instead of saying, here's the hardware, what can we do with this? If you say, here's my problem, what can the hardware do for me? It's still an improvement. We have a couple data points that show that you're in the neighborhood of a 5x improvement. The kernels are always way faster. You're up at 50x when you're doing that, but processes are not composed of kernels alone. You've got all this other stuff that you have to do. So in the end, it came down to GPUs are 5 times faster. Still not fast enough. We start clustering machines. So we have a render farm with a dozen systems packed with CPUs and GPUs and all of this. And we're running things on that. And that was the state of things last year. And it worked, but this is the differences between theory and practice. In theory, it's just keep working perfectly all the time. In practice, we ran into a lot of issues software-wise because it was tied with our graphics rendering stuff. As we improved the game, we had a horrible tendency to break the render farm systems on there. The render farm systems were just a lot less reliable than you'd expect when we had sort of rack mount stuff with these big, fat, big, hot GPUs stuck in them. And then the real thing that surprised me when I was like, well, can't we just buy more systems on here? It turned out that in many ways we can't. This was an eye-opener, really, when I said, well, let's just get 8 or 16 more render farm systems. The costs justify it. We'll keep the level designers waiting less. And we find out that we're essentially at the power and cooling capacity of our building. We can't just throw more systems in. And that never occurred to me before. Right? It's just X thousands of dollars. Can't we just write the check and get the machine in? And it turns out that we really can't. So that realization led me towards investigating another one of those wonderful hot technologies that you hear a lot about, and that's cloud computing. So late last year, early this year, with the intention of being able to run the stuff on Amazon's EC2 cloud, I started back converting all of our processing from running on the GPU to running on the CPUs. And this was an interesting journey. At the start, I figured that, okay, we're running on a GPU, let's try and just sort of software emulate the GPU. And I got a software rasterizer from the rad gaming guys called Pixomatic, which was written partially by Michael Abrach. He was an old software guy. So it was a neat tie. I got that. I started putting it in. It was going pretty well on there. But we were running into still a number of issues. It was only a 32-bit system. We couldn't use it on the big memory ones. We were still having precision issues with shadow buffers and all this and that. And finally, I just sort of bit the bullet and said, all right, we're on the software side. Let's just stop rasterizing. Let's just ray trace everything. Do a little bit of rasterizing for where I have to, but just throw lots and lots of rays. And it was really striking from experience about how much better a lot of things got. There are a lot of things that we live with for rasterization, as we do in games with making shadows, trying to get shadow buffers working right, fighting shadow acne versus Peter Pan effect on here, and this balance that you never quite get as things move around, dealing with having to vastly oversize this, trying to use environment maps for ambient lighting. And these are the things that people just, you live and breathe them as games and you just accept that this is the way things are. These are the issues and things will always be like this, just getting higher and higher resolution. But it was pretty neat to see a lot of these things just vanish with ray tracing, where the shadows are just, the samples are right. We don't have to worry about the orientations of some of these things relative to other things. The radiosity gets done in a much better way. There are far less artifacts. And as we start thinking about things in those terms, we can start thinking about better ways to create all of these different things. So that experience has probably raised, in my estimation, a little bit the benefit of ray tracing in the future of games. Again, there's no way it's happening in this coming generation. The current platforms can't support it. It's an open question about whether it's possible in the generation after that. But I would say that it's almost a foregone conclusion that a lot of things in maybe the generation after that will wind up being ray traced, because it does look like it's going to be performance reasonable on there, and it makes the development process easier, because a lot of problems that you fight with just aren't there. There's a lot of things that, yeah, it's still, you could go ahead and render 5 times or 10 times as many pixels, but we're going to reach this point where are 10 times as many pixels or fragment samples going to give us that much more benefit, or would we really like to have all the local shadows done really, really right and have better indirect ambient occlusion, or even just having the reflections and highlights go where they're supposed to instead of just having a crummy environment map that that reflects on the shiny surfaces there. So I can chalk that up as one of those things where I've definitely learned some things in the last 6 months about this that have modified some of my opinions there. And the funny coming back around about that is, so I've gone through a couple stages of optimizing our internal ray tracer, and this is making things faster. And the interesting thing about the processing was, what we found was, it's still a fair estimate that the GPUs are going to be 5 times faster at some tasks than the CPUs. But now everybody has 8-core systems. And we were finding that a lot of this stuff running the software on this system turned out to be faster than running the GPU version on the same system. And that winds up being because you get killed by Amdahl's law there, where you throw in the very latest and greatest GPU, and yeah, your kernel now goes 10 times faster. The scalability there is still incredibly great. But all of this other stuff that you're dealing with, our virtualizing of textures and managing all of that, did not get that much faster. So we found that the 8-core systems were great, and now we're looking at 24-thread systems where you've got dual-thread, 6-core, dual-socket systems. Now this is just insane. This is an incredible amount of computing power. And that comes around to another important topic where PC scalability is really back now, where we went through sort of a trough where the performance that you could get out of a PC for various reasons, we had stopped scaling in clock speed. The GPUs can still throw more and more triangles and more pixels on there, but throughput in many ways about trying to get the latency cycle down was not doing all that great. But now there are a couple key factors that are making me really excited about rethinking our software architectures so that we can develop better on the PCs. The first one is 64-bit and large amounts of memory, where it is surprising how it wouldn't have been that many years ago when 4 gigs still sounded like a lot of memory, and 32-bit address space seemed ample, and it's really not. And we've got more and more things that we need much more space there. But one of the great things is memory is cheap and easy to scale, and if we can do things that makes the software development process work better by putting in 32 gigs, 64 gigs, 128 gigs, these are probably justifiable things, because it's always great to have a way to spend some more money and get more productivity out of it. We've been at the limit in terms of CPU scalability for almost all problems for years now, where the fastest CPU for a lot of problems you could buy was some person's gaming rig. It was not a Cray supercomputer. Everybody loves the lore of the big water-cooled supercomputers, but for only a very tiny subset of problems could you actually spend more money and get faster performance. Now, there's lots of cases where this is too damn slow. Can we write a check and fix this? And for most things, the answer was no. There really wasn't a way that you could just go and get something better there. But with the advent of large-scale multi-core and large memory, we have a couple axes where we really can go ahead and buy a better system and make lots of people more productive or get lots of work done in faster times. So the structure of a lot of things that we're looking at are things that can play to those strengths, either playing off lots of cores or playing off lots of memory. And I can see now, as we look back to the decisions at the start of the InTech 5, there were some things that, in retrospect, probably hamper us a little bit now, where we tied our development platform too closely to our deployment platforms. where we were looking at the PC and the consoles. They were all roughly the same power. We were looking at this where we knew the PCs were going to get faster, but it was convenient for our software architecture to kind of treat our PCs the same way as the consoles. And we eventually started trimming out and not compiling a lot of the tools on the consoles and doing more building on the PCs. But we should have made a stronger distinction there between something that's built for deployment and something that's built for development. And that's one of those things that I've gone back and forth on over the years, where in the very earliest days we had Next Step workstations for development and we deployed on DOS PC boxes. And we kept the separate architectures for a number of products. And then with the Doom 3 generation, we're like, well, every deployment platform that we're looking at is our workstation. There is no distinction here. You have the same graphics card. You have the same memory. We might as well build everything together. And that helps. There's a reason that like most kernels are monolithic and so on, because the development process is easier in many ways than having to, in college you learn that it's always better to abstract things into these black boxes and communicate. And sometimes that's true, but it's not always true. There are practical matters why you may want to just have things all mashed together. But I do think that we're sort of past the point where that's paying off the best dividends now. We need to start looking at how we can separate those things out and play to the strengths of these PCs, which are not looking much like the consoles. When we started, our desktop PC looked a lot like a console in terms of power. But now when we're looking at a 24-thread, 32-gig system, this is not a 360, and it should not be programmed like one. We should be looking at very different things on how we go about that. So, the PC, I know it's been hard for a lot of the QuakeCon crowd to see id sort of drifting into being console developers on there. I know that our PC roots have been such that we grew up there. We still, it's a struggle to get people to play on the consoles at the office like they should. We're still a PC crowd at heart, but the reality is, the consoles are where most games get played now, especially most action games and shooters like what we're doing. So that has to be really important, where it is not going to go back to the way it was where we just do the PC and we let some other company kind of, put out a console port with minimal oversight from us on there. The consoles have to be our top deployment strategy, but we do have to start changing our development strategy to kind of leverage more the strength of what we can do internally. And, there are things that I want to roll in across even the Intech 5 generations here, but I'm starting to look at what we could really do differently in the future. And some of the stuff, interestingly, again, it comes around and ties back to work that I do on the iPhone, where it's that whole axis again between specialization and synthesis. And I've got a lot of good points where I can point to the value of synthesis, where one of the things that was useful about the iPhone platform is every time I look at a new platform, you take a look at the strength and you say, what assumptions have you been carrying around that may no longer be relevant to this platform? And the distinction that we've got on most of the mobile platforms now is you've got a lot of flash memory and you've got a decent amount of RAM. On the iPhone, you've got the particular somewhat annoyance about the memory management is not really under your control. But the interesting thing there was, in that case, when you've got a lot of flash memory, a lot of situations that you would never do in a PC game, let alone a console game, when you're dealing with hard drives or optical drives, you can wind up doing them, and it actually makes brilliant sense on a platform backed by flash to do a lot of things with memory mapped files and static assets on there. Only really games that didn't have a tight interactive timing loop on them would wind up thrashing to virtual memory or something on a PC in normal cases. But I'm finding that all of the new iPhone stuff that I've been doing is all carefully architected so that all of your data winds up just being static and being mapped there. Although, like for the Rage stuff, I'm also using unbuffered file I/O to completely bypass all of that as I move around in different areas. But that notion of turning more and more of your data into something that really is static, that can just sit there, because as we come back to the lots of memory on the PC side of things, if you've got 32 gigs of memory, the idea should be that your assets come in first thing in the morning, you run around and do this, and then they stay there. And I have as sort of a goal for sort of our internal future development that if we can wind up doing things where there's really no processing done when you load something, it's just a matter of mapping something that's in the file cache, figuring out how to have